All right. Welcome, everyone. I'm Corey. I'm a software engineer here at Databricks, and I'm here with my teammate.
Hi, I'm Ben. I work with Corey.
Awesome. Now that we have that out of the way, I have a super exciting talk for you all today. We'll be covering advancements in open source LLM tooling. We're going to be spending a lot of our time focused on a variety of projects, most prominently MLflow. We'll cover a number of topics together, beginning with an overview of MLflow, LLMs, and the machine learning lifecycle. After that, Ben and I are going to take you through data preparation, training, and deployment with LLMs. We'll talk about what's changed now that LLMs are prevalent. We'll talk about challenges that arise from those changes. And we'll introduce that variety of open source tooling to help you meet those challenges each step of the way. You'll see a variety of compelling demos. And finally, you'll learn how to get started with MLflow and open source LLM tooling. With that, let's dive right in. We'll see how LLMs have transformed the machine learning lifecycle. Pun intended there on transformers models. From classical machine learning, there's typically a four-step process that application developers go through when doing machine learning. You start by collecting raw data from a variety of sources. Once you have your data, you then clean and structure it in a data preparation phase. After that, you try out a variety of machine learning algorithms, parameter configurations, and libraries to build the optimal model. Once you're satisfied with your model, you then deploy that to production, whether for batch inference or real-time scoring. That production application receives new data, which is then used to build the next iteration of your models. And as you might imagine, each step of this process has its own set of tools and its own set of techniques. For example, feature engineering with Spark or SQL for the data preparation phase. Model training leverages hyperparameter tuning as a common technique. I might use it to explore a bunch of decision tree configurations in XGBoost or classification thresholds in scikit-learn. And then finally, onto deployment. Containers at scale are provided by a variety of tools, such as Databricks model serving, Kubernetes, and more, for highly scalable real-time inference. Now let's take a look at how LLMs change the picture a little bit to create what we call the LLMOps lifecycle. Now structurally, the first thing we'll notice is we still have the same four stages. We're going from raw data collection all the way through to deployment. But what changes radically is the set of techniques and the set of tools for each of those techniques that are being leveraged. For example, in the data preparation phase, data indexing, which we'll talk about in a moment, has brought a variety of vector databases into the data prep ecosystem. When it comes time to train a model, you might be used to initializing a set of random weights, taking a large volume of data, and using it to build a very domain-specific model for your use case, and then repeating the process as your requirements change. Techniques like fine-tuning adjust that picture. Instead of using a very large volume of data, you can use less domain-specific data to adjust a pre-existing model and produce strikingly good results. Taking that one step further, prompt engineering removes model weight adjustment from the equation entirely. Without making any changes to a model, you can effectively achieve the result you're looking for. A radically different definition of the term training. At deployment time, containers at scale continue to be very prevalent, but there's this additional element of context retrieval. Given an application input, find additional documents and information that increase the likelihood that your model produces a specific, accurate response. So now more than ever, it's extremely important to have a machine learning platform that's robust and compatible with this huge ecosystem of LLM tools that's constantly evolving and supports the latest and greatest techniques. So as we do a deeper dive into the various techniques and libraries that implement them, we'll see how MLflow helps to standardize LLMOps each step of the way. And before we can move further, I'd like to recap the existing MLflow open source platform. MLflow is the only open source end-to-end machine learning platform compatible with any programming language and any library. It standardizes raw data collection all the way through deployments with a variety of helpful components, most prominently MLflow tracking for experiment management, MLflow models for model packaging and deployment, the model registry for collaborative model management, MLflow projects, which delivers reproducible ML execution across environments, MLflow recipes, which provides production-grade templates for data science, and last, but certainly not least, our brand new MLflow AI Gateway, which Ben will be talking about in detail, that delivers managed AI building blocks. MLflow is very actively contributed to, with nearly 600 contributors from the open source community. It's widely adopted, with over 2,000 organizations using MLflow on a weekly basis, and it's heavily downloaded, with more than 11 million monthly downloads. With the platform overview out of the way, let's take a look at data preparation with LLMs. In order to talk about data prep, I think we need to understand the characteristics of the data that LLM applications work with. First and foremost, LLM data is typically unstructured. For example, if I'm building an application that can answer questions about Spark, the inputs to my application are sentences, unstructured data. It's variable in content, variable in length, and the responses are similar. This is in contrast to a lot of classical machine learning techniques outside of natural language processing that typically consist of a well-defined data schema with types and narrow ranges. Following from this, LLM applications often deal with a large domain of inputs. For the same question answering example, there are a bunch of different questions that I might ask about Spark. And there are a bunch of different ways that I could phrase the exact same correct answer. Further, context is more important than ever when dealing with LLMs. For example, if I'm asking a Spark question, why did the driver stop suddenly? And I feed that directly to a general LLM like GPT, it's quite possible that I get an answer about driving automobiles and why one might stop. So providing that additional context to tailor the output to the domain I'm working in is extremely important. And finally, as I alluded to before, there can be multiple correct outputs or answers to a query. Consider text summarization. If I want to build an application that summarizes customer support tickets, either of the two examples shown on the slide are semantically equivalent, perfectly valid ways to begin my summary. As a result, it's hard to come up with a ground truth label for my applications that I can evaluate new configurations against. So now that we understand our structure of data a little bit, let's take a look at solving that problem of context. We can consider that query from the previous slide, why did the driver stop? We're referring to Spark, but how can we change our query so that the large language model knows that? Rather than feeding the query directly into our model, we can first retrieve additional context, documents that are relevant. Given the query, we retrieve those documents, feed them to the large language model, and we get back a domain-specific answer. This one about the Spark driver node. It's much more helpful. This process of extracting documents and associating them with a query is called document indexing and index querying. And let's take a look at how we can build this kind of workflow with just a few lines of code. To build a document index, all I'm going to do is start with my collection of documents, for example, in a Delta table. I'll take those, I'll feed them in to an LLM of my choosing, whether proprietary or open source, and I'll compute embeddings. These are vector representations of the documents. I'll then store those in a purpose-built vector database. And that's all there is to it. I have a database full of embeddings, and I can then proceed to query it. Before I do that, we can see just how easy it is to create this kind of thing. Open source tooling, like Llama Index, makes it extremely easy with just a couple of lines of code to perform this procedure on large-scale data. LangChain, which integrates with a variety of open source LLMs and supports a wide variety of vector databases, makes it just as easy. So now I've built a document index. What do I do next? All I need to do is query this in my application. It's that simple. So I have my query, why did the driver stop? I'm going to do the same thing I did before. Feed that into my LLM of choice. get back the embedding, the vector representation, and then do a lookup in my index. Find the documents corresponding to the most related vectors and pull them out. That's all there is to it. I can obtain 5, 10, n, an arbitrary number of related documents, providing that additional context that an LLM can use to give me a tailored response. And querying with Llama Index, as well as LangChain, is just as easy. Highly recommend checking out some of these open source tools for retrieval-augmented generation and creating and querying document indices. With LLM data prep out of the way, and us having a good understanding of some of the techniques and data characteristics, let's move into training with LLMs. The first thing we'll note about LLM training is that there are a lot of new opportunities that may use slightly less data and take less time compared to classical machine learning. Obviously, with the prevalence of open source LLMs, we encourage folks to explore training LLMs from the foundation, but you have many other options. For example, fine-tuning on specialized data, as we talked about several slides ago, can produce significant performance improvements with relatively low data volume. And prompt engineering doesn't require any additional training data at all. With less data comes less change or iteration on model weights. So if my model's weights aren't changing as much, what is changing? Well, that's the inference logic surrounding that model. I'm going to change what I ask my model to do, the instruction set or the prompt. I'm going to change the expected output format for my answer, the particular length, the level of creativity, and beyond. Fortunately, it's much easier to make these kinds of changes than it is to retrain a model from the ground up. I don't have to wait for a large neural network to converge for several hours before testing my change. As a result, I can create hundreds, even thousands of model candidates in the time that it used to take me to produce one. With that comes an additional challenge. Nothing's free. There's now a greater emphasis on model evaluation. I have to take each of those 1,000 model candidates and determine whether or not I've seen a performance improvement. I also have to make sure that my models aren't introducing risks when I go to deploy them to production. Because we're dealing with unstructured data, you have oftentimes string inputs, string outputs. There's typically a human-in-the-loop procedure here. You need to manually inspect those inputs going into your models and the outputs across several different configurations to truly assess the performance. Now, there are some metrics that help that you can compute on a per input-output basis or aggregate metrics, but there really isn't an excellent replacement at this point for manual human-in-the-loop evaluation. And to keep track of this at scale, it's very useful to be able to annotate certain outputs as good, bad, neutral, better, or worse. With the training overview, let's take a look at prompt engineering as a key technique. As a data scientist or ML engineer, the first thing that I'm going to do if I'm building an application with prompt engineering from the ground up is have an input or two in mind that I want my application to perform well on. For example, considering question answering, I'm going to go back to that question about the Spark driver. Why did the driver stop? Then I'm going to write a set of instructions or a prompt to instruct or tell the model how to respond to that query. I'll choose the collection of parameters like response length and level of creativity, and I'll pass that into the LLM, producing some result. If the result is to my expectation, then I'll try additional inputs. If I don't like what I'm seeing, I'll go back and change the instructions, the prompts, and the query parameters. Over time, what I'll find as I develop models that perform well is I create this data set of expected outputs. Every additional model that I try and configuration I iterate on is then going to be expected to do at least as well as past models on these given inputs. Initially, you don't have much benchmark data, but if you do prompt engineering using this iterative procedure for a few hours or a couple days, what you end up with is a robust evaluation data set. Now, when starting with prompt engineering, we typically recommend optimizing for accuracy first. At the end of the day, the goal is to deploy an application that meets customer needs. So typically what we'll find is that folks start with the state-of-the-art models, for example, OpenAI GPT-4. They then iterate on the instructions or the prompts to identify an optimal instruction set. So if I'm asking my application to answer questions about Spark, I may instruct it to answer the following question about Spark appearing between triple backticks. It's a decent start, but I might find that the response is a little bit lengthy or verbose. I could update that to tell it to be concise, which will shorten the response, but perhaps I need an additional level of detail or some code examples. So from there, in addition to being concise, I can tell the model to include references to the Spark documentation in the answer. I iterate like this until I'm happy with the performance on a particular prompt template, but I'm not done. The next step, once I have a baseline level of accuracy, is to minimize cost. If I'm going to take this application and put it on the Spark website for every Spark user to query, I really need to make sure that that fits within my budget. So what I'll do is compare the performance of the same prompt between the state-of-the-art set of models from one vendor and the state-of-the-art models from another vendor. If I'm seeing good results, I'll move into open source models. For example, I could try a large open source model, MPT, with 30 billion parameters and see if that performs well, and move into smaller and smaller models until I find an optimal point where I'm maintaining my level of accuracy while minimizing cost. Now, you might have to make certain changes to your prompt and instruction set in order to make this work in practice, but they're typically somewhat minimal. Prompt engineering is really easy to accomplish with LangChain. In Python code, you can define your prompt template, you can choose your LLM, you can configure that set of parameters, and then pass in your queries. You can see the responses, determine how well your model is performing, and iterate from there. But one observation that we've made while developing MLflow is that you could do all of this without any code at all. We're excited to announce that in the upcoming MLflow 2.5 version, we'll be introducing a prompt engineering UI that removes code from the entire iteration process. The first thing that I can do with the prompt engineering UI is select an LLM that I want to develop with. For example, I'll take the open source MPT-7B model to start. Then I'll fill in my prompt template. For question answering, it's a question and some additional optional context. I'll set a response length and level of creativity for the response, and then I'll try this out. I can put in a query by filling in the variables in the template, click the evaluate button to test that out, and see the result. I can iterate in this playground environment until I get something that seems to be performing fairly well. And once I'm happy with it, I can record that to MLflow tracking. That recorded model can then be deployed all the way through production environments for real-time scoring and batch inference with a simple click of a button. Because we've made it really easy to iterate using prompt engineering and build a bunch of model candidates, evaluation then becomes extremely important. Fortunately, MLflow covers this as well. In MLflow 2.4, we extended the powerful MLflow Evaluate API to support LLMs natively. In the code example on the left, we can see that we're loading a benchmark dataset for news summarization, and we're specifying a particular summarization model that we've built and want to evaluate. We put those together, send them into MLflow Evaluate, and with a single function call, we get all of the outputs for that model on that data set. We record them to MLflow tracking, where they're visible in our UI, and we automatically compute domain-specific metrics, in this case, Rouge, perplexity, as a measure of how easy it is to interpret the summary, and beyond. All of this with just that one call to MLflow Evaluate. On the right side of the slide, we can see our brand new evaluation UI, where we can seamlessly compare multiple model configurations and how they perform for the same exact input. Now let's bring all of this to life with an interactive example. Opening the MLflow experiment page, the first thing that I can notice is that the evaluation tab is now visible in that UI. I'll go ahead and click on the evaluation tab, and I'll see that for the Spark question answering example, I have a couple of existing models, and they've been evaluated on 3 questions. What is Spark? What is Spark Connect? And the tangentially related, what is MLflow? I also see that there's this new button that I can use to create a run. I'll go ahead and click on that. I'm going to move forward, click on my run, and I immediately see this new prompt engineering UI. For the purpose of the demo, I've pre-populated this with my choice of LLM, MPT30B. I've filled in the relevant prompt template for my application, configured my query parameters, and dropped in that example question, what is Spark Connect, with some additional context that helps tailor the response. I can then go ahead and click on the Evaluate button, and in real time, we're going to see that the prompt output field responds, and I can assess the quality of that model. It may not be perfect, but for the purposes of a demo, it's good enough. The response starts well, it gets truncated at the end, but I'm going to go ahead and save it just so I can see how it compares to additional model candidates. So I'll go ahead and move down to click this log run button. This records a new run to MLflow containing that choice of LLM, query parameters, and prompt template. My evaluation tab then refreshes, and I can see this output for what is Spark Connect with my new model side by side and compare it to my pre-existing configurations. All of this is extremely seamless. I didn't have to write a single line of code. Now with that, I'm going to hand it over to Ben to talk a little bit more about how we're packaging these models for LLMs. Ben is also going to walk you through deployments and the AI Gateway.
Thanks, Corey. Hi, everybody. So one of the things that we've been working on with the release of MLflow 2.4.0, I guess that was like a couple months ago, was the ability to provide native support for a couple of new flavors. And flavors, for everybody that's familiar with MLflow, it's sort of the named entities that we use to package up artifacts and log metrics, parameters, tags, all the data that we need as data science practitioners to keep track and lineage of what we're actually working on. So with the LLM support that we've created, the demo that we're going to show in the next slide is specifically around supporting Hugging Face transformers, but we also have provided native support for LangChain that you saw Corey demonstrate on some of the previous slides, as well as OpenAI as a native flavor. But we've tried in these flavors to kind of keep the same sort of feel that all the other flavors have, even though the paradigm is different about how we interact with these models and how we train them. So the standard interface, it should feel like other flavors, and it should just feel like it's part of MLflow, even though you're working with a completely different sort of artifact in a training process. And particularly with transformers, we've made a decision in the implementation details of supporting two major paradigms. One is to make everything sort of pipeline-centric. It's a higher level API, it's a little bit easier to work with, it sort of streamlines everything. But also to provide sort of low-level support for component level. You won't see that in the demo in a moment, but if you check it out within the repository, you'll see how it works. So in this demo, you're going to see a very simple high-level application of a Whisper model. We're going to download it from Hugging Face Hub. We're going to get it within our cached environment. We're going to pull the data set in byte array data, a sound file from NASA. And then we're going to log MLflow, a model of that transformers type, providing some specific information during logging time that we call inference configuration. And that's going to configure that instance of that model with a bunch of defaults that are going to be how users will interact with that. And it'll be sort of locked to that instance, that run. So what you're seeing here is just some imports at the top. We're getting that sound file. We're downloading a transformers pipeline and constructing it. And we're also using a signature inference that we have as well. And that's pretty important for these type of models so that you can tell end users and the actual systems that are going to be hosting these what sort of data you're expecting. And the demo's going through pretty quick, but what it did was it pulled the Apollo mission log of the actual takeoff of when we landed on the moon, because that's a cool sound file. And Whisper transcribed it pretty well. We showed the two main ways of interacting with it, just like with every other MLflow model that's out there. You have the native support, you load the model, you actually run predict or inference on that actual native version of it, but also showing PyFunc support, which is how we're going to be doing serving as well for these, for inference. Now, when we're talking about LLM deployments, as Corey was mentioning earlier in the talk, there's some things that we have to think about that's slightly different than other sorts of models that we would deal with as a data science practitioner. You know, we're talking about something like an XGBoost model or a linear regression or logistic regression. These sorts of models are pretty tiny. They're pretty quick to train. They're not exactly quick to get good and get good results, but we're not dealing with a vast amount of data. All bets are off when we're talking about LLMs, though. Some of these pre-trained open source models are truly gigantic. You're talking about gigabytes of data for each of the different portions that make up the actual object that we see as a model. There's many files that are involved there. And it actually becomes a bit of a problem when we're talking about coupling the fast-paced iteration of stuff like prompt engineering or fine-tuning, which you saw in the keynote this morning. They're talking about, hey, it took us 9 days to train one of these from scratch, which is basically initializing a model, feeding it all the data, trillion tokens worth of data so that it understands context about language. And then each of those different iterations that they're doing from that pre-trained model where you're fine-tuning for a particular use case on bespoke data. That's sort of what the MLflow flavor is designed for, is that fine-tuning as well as the prompt engineering. But that whole process is pretty quick. You can fine-tune in less than an hour on sufficient hardware. So you can generate a lot of copies of these very quickly, and you can rapidly get to a point where you're like, hang on a second, this is kind of expensive. There's got to be a different solution for this. But as we showed it earlier in the inference deployment of this with the document index search, we have model inference set up just as it would be in any other MLflow deployment paradigm, where we have that model inference reaching out to different hosting services and being able to make those calls. And when we look at the entire ecosystem of what is supported right now currently in MLflow 2.4 and the upcoming MLflow 2.5, there's a lot of different disparate systems that we're now integrating with. We have transformer support for OpenAI. We have integrations with other providers, such as Anthropic. We have LangChain support. And all of these things can be accessed and interacted with PyFunk and very simple high-level APIs. When we start talking about the prompt engineering, when we're iterating on the development of these models and trying to get something that's going to solve our business use cases, we're creating multiple different versions and candidates, and we need to evaluate them. Sometimes we need to actually push these out into production and have a bunch of different versions that are available for people to interact with. Now, when we're looking at this from a getting started point, that's when we start on projects as ML practitioners, we start thinking of, okay, what is the first couple of weeks? What is the P0 of our release of this new feature? Not too many people think about, what does this look like a year from now? Or what does this look like 5 years from now? And anybody who's been doing it for long enough and has to maintain a bunch of stuff in production, you suddenly go from that day one, super excitement, everything's clean, like, hey, we got these 3 models in production, they're great, and everything's working really well. And then years later, you're like, what is prod? I have 173 models, different versions. Nobody cleaned this up. Ben was super lazy and didn't delete a bunch of stuff. We still have stuff running in prod. When we're talking about hosting like XGBoost models, no big deal. It's not, nobody's going to notice. Our CFO isn't going to come knocking on our door saying, what are you people doing? This is super expensive. Shut it down. But with this, I promise you that will happen. When you're talking about hosting VMs, GPUs, you have all of this data that comprises that model. You need a sufficient VM size to run that. You need enough memory to hold these things. So we're not talking about dirt cheap VMs. These are the most expensive of the most expensive things that are out there on the cloud. The price is coming down, but it's not really going to be as cheap as what people are thinking. So one of the ways that we can handle this, and what we've designed over the last 8 weeks, 7 weeks, we designed a system that allows minimization of that cost, and also adding a little bit of command and control to it in order to simplify that problem, because that is a very serious production level problem that we want to help our users avoid. And what we call that is the MLflow AI Gateway. And it allows us to effectively host a model or an instance of a model, and then interact with a configuration that we supply, and we call them routes. And we'll actually set that up so that we have a single point of user access. And that could be users of yourself. You, as a data scientist or an ML person, you could be the one that's interacting with the AI Gateway. It could be your customers, could be analysts at the company, it could be people in marketing, whoever is going to be interacting with this thing that is being hosted, or it could be services, it could be applications that you're building. But it provides that single point of contact so that it's easier to manage what is running right now in production and be able to change that without having to write a ton of code. And the 4 main things that we're looking at for the AI Gateway for MLflow is protecting your bank account is the most important one, or that your funding for your team, by credential management. With some of these service providers, you have an API key that's issued that's linked to a credit card or an enterprise account. Not the best idea to really want to move fast and go crazy because everybody's all hyped up about how amazing these things are and they're saying they want to use this. And the ML engineering team or IT ops are the people that are issuing keys. You don't really want to issue 20 keys to 800 different people and hope that they know how to manage those correctly, that they're not leaked in code, that they're not used inappropriately. So the gateway provides credential management. Something else we're looking at is caching, the ability to frequently issue queries that you want to basically not have to make an outside API call to a service. It would be able to return the same statement that's already been requested. Logging is a big one as well. So if you want to, as Patrick was talking about in his keynote earlier this morning, that fine-tuning process is super critical for you to be able to issue a bunch of queries, get the results back, make modifications, apply labels to them, and use that for retraining. So we want to make sure that that's as simple as possible. And also the ability to rate limit people. You can imagine with the cost rate for some of these providers that are out there, if you don't have the ability to restrict how people are using it, one of the users could issue something like an embedding request for 200,000 documents, and you just spent a ton of money, and that could have been an error, or they could have been testing something. You just blew through your week's budget that you had. So being able to provide a limitation or forced limitation to the number of requests that are sent to basically protect your bank account is super important. And making sure that we can have a set quota for a particular route endpoint and have that configured as part of the gateway is going to be critical. So in order to show you how simple this is, what we've built, we're just going to go through a really quick configuration. It's all YAML-based. And what I'm going to do here is we're going to create the config, and we're going to use everybody's favorite text editor, VI, create that YAML, and you're going to see me type really fast here. But I'm creating a bunch of different routes here, 3 of them, one of which is GPT 3.5 Turbo, which is an OpenAI provider, and that's going to be the chat endpoint. And notice here this API key, we're referring to an environment variable. So keys are never leaked. They're set on that VM where the gateway is running. You don't have to share it with users. They can hit this gateway and get authentication that way. We configure those 3 routes, 2 OpenAI routes, 1 Anthropic route, save that config.yaml, and then with a simple CLI command, MLflow gateway start, provide the location to that config file, tell it where the host and port is, hit enter, and your gateway is up and running. And one of the benefits of what we built, the back end for the gateway, is that we use something a little bit more modern than what the rest of MLflow servers use. We decided to go with Unicorn and Fast API. One of the reasons for doing that is because all of these calls are, it's better if they're asynchronous because there's a lot of waiting that happens when you're talking to these providers. It's a long-running query. We don't want that to be blocking or synchronous. But another great benefit is the fact that we get Swagger docs for free. You can go to your gateway server address /docs. You get to see this. You can interact with it in real time. You can see what endpoints are configured, and you get ready-made docs for your particular deployment. And you can see at the end, we have the 3 routes that we configured in the configuration. Another thing that we built as part of the MLflow gateway, just like with regular MLflow tracking, is the gateway client. And what this allows us to do is set basically the configuration to our gateway server itself, and then generate this client, which is a very high-level API that exposes things like a search routes functionality. See, what can I actually query? What are the characteristics of that? What is the metadata associated with that route? And we can get information directly from a particular route by just querying it by name. And then when using this, we can go through and write in very simple Python code without having to worry about connecting to an SDK or doing anything where I'm having to read through a bunch of docs to figure out, like, how do I query OpenAI's SDKs. You can hit that client and just do a query of the data structure that's required, and you're going to get your response directly in a notebook or through any other automation that you have. We also, in the return type of each of these, create a standardized metadata payload so that you can have lineage of where that actual response came from. You can see where did I send this thing, and how many tokens did I use. If you're hitting certain providers, it'll return stuff like that so you can monitor cost. And it'll give configuration information about our actual gateway config, so you can see what route was queried for this. Included with this is also the Fluent API. Just like with MLflow tracking, we also have this higher level, slightly easier to use syntax sugar Fluent API, which doesn't require generating a client. That's managed for you automatically. You just need to provide your actual gateway connection details, and then you have all of these higher level functions that you can call and get the same sort of response. And that's pretty much it for the demos for that. And coming soon, with the release of MLflow 2.5, is that MLflow AI Gateway. It is still in experimental, which doesn't mean that we're going to delete it or anything. It means that we're still actively in development of that, adding new features all the time. That's going to be growing, and we're going to be responding to community feedback for things that people want to see in that. The prompt engineering UI that Corey showed earlier, the MLflow Evaluate with all of those awesome tools that come with evaluating the responses of these. And we're also going to be adding some longly requested ability to add inference parameters for PyFunk. That's very critical for LLMs, but it also works for other flavors as well.
Awesome. So now that we've covered all of what's new in MLflow for LLMOps, we've told you about the ecosystem, introduced you to a bunch of open source tools for LLMs, we really encourage everybody to get started with MLflow for LLMOps. Super easy to install, just a quick pip install MLflow. We've linked our GitHub repository. Please try it out, send us feature requests, let us know if we have any bugs. You can visit our website at mlflow.org, join our Slack, and check out plenty of examples on our GitHub repo and our docs. Thank you so much for attending, everybody. Really appreciate the attention.